Previously, I think we had considered heating times in terms of stochastic processes in general. But in this video, still as we still continue talking about Brownian motion, we'll be looking at heating times in Brownian motion in the as we continue talking about the stochastic processes playlist. So heating times in Brownian motion is a subject here. And before we continue, we want to do a quick refresher on the idea of Brownian motion. So first of all, remember that a standard Brownian motion B of t for t greater than or equal to 0 satisfies the initial condition that B sub 0 is equal to 0. That's at time 0, the motion is 0. Then there are independent increments. And then bt minus bs is normally distributed with mean 0 and variance t minus s. And then it follows continuous paths. Then, talking about heating time now, the heating time of level A is defined as tau sub A. So, and that gives the infimum of all t's greater than 0, such that the Brownian motion at time t is equal to that A. So, this represents the first time the Brownian motion reaches level A. That's the heating time of level A. So, and then talking about the key properties of heating time, we have all this. First of all, we have for almost sure heating, for almost sure heating, we have that okay, I guess I can go bit by bit. Wanted to share everything. So for almost sure heating, probability that tau of A is less than infinity, that is, it is defined, is equal to 1. So Brownian motion will eventually hit any level. And then B, we have density of heating time. So for A greater than 0 now, for heating time greater than 0, then F sub tau sub A of T is A over square root of 2 pi t cube e raised by minus a squared over 2t for all t greater than 0. So that's the density of heating time right there. And then we have the scaling property t sub a, which is a squared tau 1. Then we have infinite expectation, where the expected value of t sub a is infinity. And then we move on to reflection principle. Reflection principle, of course, we talked about reflection principle in the last video, and we saw how that is helpful. So we're able to get some probabilities like that. So for a greater than 0, probability that tau of a is less than or equal to t is equal to probability that the maximum value of b sub s for s lying between 0 and t is greater than or equal to 1. So probability tau sub a less than or equal to t is equal to probability that the maximum of b sub s is greater than or equal to a, like that. So using the reflection principle, we can then say that is probability that tau sub a, probability of tau sub a less than or equal to t is the same thing as 2 times probability of b sub t greater than or equal to a, which is then equal to 2 into 1 minus 5 into a over root t. So I did we had several examples of this in the last video. So you want to check that out in case you didn't get, you've not seen the video on reflection principle in Brownian motion. So talking about example 1 now, probability of heating before time t. So what's the probability that you're going to heat before time t? So we compute probability that tau sub a, the probability that the Brownian motion is going to hit level A before time t. So we want to compute that as 2 into 1 minus 5 into a over square root of t. So for the numerical example, let's say a is equal to 1. So let's say level a is 1 and t is 2. So we know that a over root 2 is 1 over root 2, which is approximately 0.707. And then phi of 0.707, this is cumulative frequency. And of course, you can use tables to get this, and if you have access to the internet, you can just say cumulative distribution frequency. Yeah, it's a phi, right, of 0.707. Okay, you can just do that, and you get 0.7602 like this. So you can go all the way down and see all the steps, and the answer, everything still goes back to 0.70 0.7602, right? So that's why you have this approximately 0.760. So probability that tau 1 is less than or equal to 2 then is approximately 2 into 1 minus 0.2760, and that is equal to that's approximately 0.48. That's probability of 48% that you hit level A before time, the heat level 1 before time is 2. So the time can now be whatever time measurement you are using, maybe seconds, minutes, hours, or all that. And of course, so this simulation gives us all of that. Okay, A is 1, T is 2, and then you have all this. So you get 0.4706 like that. Then talking about the density, so imagine that, this density, if you remember, it holds for positive, it has A greater than 0. So in that case, now you have F tau sub 2, because A now is 2, of T is now 2 over square root of 2 pi T cube, e raised by 4 over 2T. So if you evaluate that, you have this, it is reduced to this expression, which you can then simulate using Python. All right. And if you use Python like that, you can, so here now we take t, the time, now we allot time from 0.01 to 5 in 500 steps, and then a is 2 like we have it, and then write the density, the expression for the density, and then we try to simulate all of that. I think this is taking a lot of time because we have, um I think it should result, because okay, yeah, this one is fine now, good. So yeah, this one is fine too now. So we then have the density like that. So you have it going and it peaks and then starts dropping back over time. So that's density of heating time, A equals to, like that, for A equals to. Then we also have the idea of scaling. So using the scaling property, you have T3 going to 9 tau 1. So because A is 3 now, so for the scaling, right, the original scaling we saw, it's like tau sub A is equal to A squared tau 1. So in this case now, since A is 3 here before, because this 3 here is A, so that means 3 squared tau 1, that's 9 tau 1. So we can also simulate this now to get, okay, this is 2000 steps. I think it takes a whole lot of time. So what this simply means is that this means heating time grows quadratically with distance. So as the distance is increasing, so we have the heating time growing quadratically. So and that's why it's A squared tau 1. So well, we'll move on. So if before we finish we get the results, I'll show it. So for example 4, now we now have infinite expectation. So we analyze that expected value of tau of A is equal to integral from 0 to infinity of t ft dt. So for large t now, f of t is just now approaches 1 over t cube over 2, and then so t ft is approximately 1 over t raised by a half, so that there you can then integrate over over infinity, integral from 1 root t dt. So whatever, however you look at it, it ends up being infinity. So therefore you say that expected value of tau sub A is infinite, and that's why we talk about infinite expectation, which is one of the properties of heating times of a Brownian motion. Okay, then we talk about two-sided heating time. So if you define tau sub A comma B, equal is to be the infimum of time greater than or equal to 0 for bt equals a or minus b. All right, so that's two ends now. Then you can say that probability that hitting a before minus b will be b over a plus b. So imagine if a is 2 and b is 1, then probability that you will hit 2 first before hitting 1 would have to be b, which is 1, all over a plus b, that's 2 plus 1 3, and that's 0.333 something. So if you simulate this now, I think the other one is still running, so I suspect it may impact how this one returns, but we already know this is 1 over 3, so we can get it moving. Okay, because it's the same thing. A is 1, A is 2, B is 1, and all that. So in summary, we see that Brownian motion hits every level almost surely. Then heating time has heavy-tailed distribution. Then expected heating time is infinite. Then reflection principle links heating time and maximum. And then scaling, tau sub A uh, is follows that quadratic expression thing we talked about, like that. Where is it now? Yeah, so it's the heating time grows quadratically with distance. So as distance grows, we have a quadratic growth like that for the scaling. So and then we have some key formulas here. So the heating time to get to a tau of A is infinite. Yeah, I mean, we saw all of this before, so we can use them. And we also add some examples. So these ones are still running because I guess the ranges are so big, right? So, but we know the results already. So then for practice problems, then you can check out all of this. Let B sub T be standard Brownian motion. Compute probability that tau 1 is less than or equal to 1. So we just use the regular formulas that we've seen before. Probability that tau 1 is less than or equal to 1. So that's the kind of thing we have right here. So that means A is 1 and then T is also 1. Okay? So that's the idea here. So that's probability that tau 1 is less than or equal to 1. Then, we want to show this, compute this. Tau 2 is less than or equal to 4. So of course A is 2 and T is 4. So you want to compute that. Find the density of T3, then verify that the density integrates to 1. Okay. So you want to check this. So that's some big work on integration there. Maybe not quite big, but I see it might just be like integration by parts or something. And then use scaling to express T5 in terms of T1. Of course, T5 is going to be 5 squared T1. That's 25 T1. Then if T1 is if Tau1 is T, rather, what is the distribution of T4? That'll be 16 T. That'll be 16T. That'll be 4 squared T, which is 16T. Show that expected value of T tau sub A is equal to infinity. Then compute probability that tau 1 is greater than T, and all of this. Show that probability that tau A is greater than T is 2 phi. So, I mean, this came from the idea of reflection principle. Then we have the rest of them. Compute the median of T1 numerically using probability that tau 1 less than or equal to T is 0.5. Then let T21 be the first hitting of 2 or minus 1. Complete probability it hits 2 before minus 1. Because that will be 1 over 2 plus 1, which is 3. Then generalized probability hits A before minus B. That's A over A plus B. Is it A over A plus B or B over? Yeah, it's B over A plus B, sorry. So it means the other one I talked about, 2, 1, that'll be 1. Yeah, that's fine. 1 over 3 there. So we have all that. So show that tau sub A has a heavy tail by analyzing this, then computes all of these things. Yeah, so try your hands on them and let's see what we get. So to confirm that you really have a clear understanding of all these things. Okay, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. So if you try your hands and you think you need help with any of the questions, you can let me know in the comment section, either here on YouTube, either on YouTube or Facebook rather. And I make a video to explain whatever concept may be difficult for you. So don't forget to try your hands on these questions again: 1 to 5, 6 to 10, 11 to 15, and then 16 to 20. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel, and that gives you privileges like having exclusive right to see some videos, or seeing some videos first before others see them. You could also request for PDF copies of my notes for your personal use. We can also hang out to discuss whatever interests you on this channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. In the next video, which is the last on Brownian motion, of course, not the end of stochastic processes, we'll be talking about applications of Brownian motion, and you definitely want to see that. So, see you. Bye.